Okay, today's day one of chapter 5. My description of chapter 5, as politically incorrect as some may deem it to be, is your trig world is going to meet your algebra world, and they're going to have a beautiful love child known as analytic trigonometry. So what's going to happen is the trig concepts that we've been looking at so far, we're going to do so now with much more algebraically intensity or intensiveness than we have so far. Okay, part of the process in learning this material is we need to be comfortable with the fundamental trig identities that are from page 372 in your textbook. Now, some of these guys we've addressed in detail, some of them we've touched on, a couple of them are going to be new. So as a recap, reciprocal identities. We've known these for a while. Sine and cosecant are reciprocals of each other. Cosine and secant. Tangent, cotangent. Quotient identities. We've used these quite a bit as well. Tangent is sine over cosine. Cotangent is cosine over sine. Pythagorean identities. These have popped up a couple times. But they haven't been ultra important. They've kind of been alternatives to things that we already know how to do using other strategies. In chapter 5, these are going to be big deals. Not only big deals in chapter 5, but we're going to address some other trig-related topics a little bit later in the year, and these guys are going to be central to being able to solve those problems. So the Pythagorean identities are going to be pretty big deals. Okay, two new sets, cofunctions and even odd. To address the cofunction identities, I'm going to go back to basic right triangle trig. So we'll just use the first one as an opening example here. If we were to rewrite that in degrees instead of radians, which if we want to address this in SOHCAHTOA trig, that's what we want to do. It would look like that. Pi over 2 is 90 degrees. To illustrate this, I'm going to sketch a simple right triangle. I'm going to label my three sides. And I'm going to choose one of my two acute angles to be my u. Okay, whichever one is u, the other one has to be 90 minus u, because the two acute angles in any right triangle must add up to 90 degrees. So, I am going to look at, well, what is the cosine of u in this right triangle? The cosine of u is going to be adjacent over hypotenuse. And then I'm going to look at what's the sine of 90 minus u. In relation to this angle, opposite over hypotenuse. And you can see the sine of 90 minus u and the cosine of u are both the same thing. So if we did this in radians instead of degrees, we can replace the 90 with the pi over 2. And I just realized that you did not see that on the screen. I apologize for that, so I'll do a quick run through. So I sketched a generic right triangle. That's my A, that's my B. My C looks like it got a little tail from a smudge there. That's my C. Choose one of my two acute angles to be my u. The other one must be 90 minus u. So the cosine of that angle, A over C. Sine of that angle, A over C. So that illustrates this first cofunction property. We could also do the sine of u. That would be B over C. The cosine of 90 minus u. That would also be B over C. And that illustrates this one right here. And you could do 4 more of those guys to illustrate the other 4. So one way to address the cofunction identities is going back to one of our first days of trig class, just working off of a simple right triangle. All right, a little bit more of a sophisticated way of looking at it would be in terms of rewriting equations for graphing purposes. So I'm just going to make up a random graph here, a random function of a graph. So f of x is equal to 5 sine of 2x plus pi over 6. Right. What if we wanted to write a cosine equation that produced the same graph as this? What we did in that lesson was we would either sketch this out by hand or get a picture of it on a graphing calculator and just kind of go piece by piece and kind of building it up from scratch in terms of, well, what do we know? What can we figure out? How can we get a cosine equation out of it? It turns out that you can use these guys in order to do that with a guaranteed set, no guessing and checking. It'll always give you an equation that works. So f of x is equal to 5 cosine. And then what we're going to do is use one of these two guys here that relate sine to cosine. Now these u's, as they appear in the identities, could be a single numerical value, like pi over 4. It could be a single variable, like x. Or it could be an algebraic expression, like 2x plus pi over 6. So what we're going to do is treat this as that whole thing as being our u. So if we want to get a cosine equation, it'll be 5 cosine pi over 2 minus that 2x plus pi over 6. And that will be one function that would produce the same graph as that function right there. So if we want, we can do a quick check just to confirm that. Get my graphing calculator, y equals, clear that stuff out. So 5 sine 2x plus pi divided by 6. Make sure that we are in radian mode for this. We are. Going to do a zoom 7 for starters. Probably need to tweak that window because we've got an amplitude of 5. So go to the window, make that like -7, +7 graph. All right, so that's a decent window that's going to show us 5 sine of 2x plus pi over 6. Now, as I already mentioned, back when we did our graphing, kind of just by visual inspection and knowing the different a, b, c, d values, we would kind of build the cosine equation from scratch. These cofunction identities will be guaranteed to give us an equation. It may not be the prettiest one, but it'll be one that works. So let's test the one I just created. So it'll be 5 cosine pi divided by 2 minus, and then 2x plus pi divided by 6. And we'll hit graph. And visually, it looks like that second graph is tracing right over the first graph. We can do one more confirmation with that. Do second table. And if you look at all the y values, they appear to be the same for both. Now, normally, if it was a final answer, you wouldn't leave this as is. You would clean it up a little bit. So to clean that up a little bit, we would clear out those parentheses by multiplying through by the negative sign. And then we can combine these like terms. So pi over 2 minus pi over 6. That will be 3 pi over 6 minus pi over 6. 2 pi over 6 or pi over 3. It will be negative 2x plus pi over 3. So that would be a little bit of a cleaner function that would produce the same graph. Now, when we were in the graphing unit, we tried to avoid that negative b term here. It was brought up some issues that didn't quite fit the narrative that we were working with there. For what we were doing at that time, it was cleaner to just use that visual inspection approach. But this is a little bit faster in terms of getting you an equation. So any sine equation could be written with as a cosine, vice versa. Any tangent can be written as a cotangent, vice versa. Any secant can be written as a cosecant, vice versa. This is one way to make it happen. There are other versions of a cosine graph that would produce the exact same results, and we did plenty of those examples back in the graphing unit. Okay, now on to the even-odd identities. All right, your book lumps them into one big category of even-odd. In terms of which are which, these guys are the evens, and these guys are the odds. And if you look at the SIGN pattern, what happens is that negative sign slides out in front to go there. This slides out in front to go there. This slides out in front to go there. This slides out in front to go there. In terms of the even identities, what happens is it just goes away. Cosine of negative u is the same as the cosine of u. All right, these identities can be addressed in a couple different ways. Just like we addressed the cofunction identities, we did so in the context of right triangle trig, we did so in the context of graphing. Here, we're only going to look at them in one context. We're going to look at them in terms of what are the visual features of the graph that cause these guys to be considered odds and these guys to be considered evens. All right, so what I have here, let me zoom out a little bit. A summary of our 6 basic trig function graphs. Right, what I did on that previous piece of paper, I told you that these guys, the cosine and the secant, those are considered to be your evens. And then those guys and those guys are considered to be your odds. All right, in terms of the visual feature that even functions have, is they have reflectional symmetry with respect to the y-axis. So if you look at the y-axis here, the left side is a mirror image of the right side. You look at the y-axis here, the left side is a mirror image of the right side. So any function, trig or otherwise, that has that reflectional symmetry with respect to the y-axis is considered to be an even function. All right, now what about the odd functions? Okay, the deal with the odd functions are they have 180-degree rotational symmetry about the origin. That's also known as point symmetry, is what some books or some websites will refer to it as. So as a quick visual for one of them, what I did was I cut out another piece of paper, that sine graph right there. What I'm going to do is rotate that graph 180 degrees. So as a point of reference, if I rotate this 180 degrees with the origin as the center of rotation, 180 degrees will be when that arrow points straight down. So if I rotate this until that, oops, let me grab that. Rotate this, there we go, 180 degrees until that arrow points straight down, you can see that it rotates onto itself. The graph looks identical to what we started with before the rotation. So anytime you have a graph, trig or otherwise, that has that 180-degree rotational symmetry about the origin, it's considered to be an odd function. So if you take this cosecant, rotate it 180 degrees, lands on top of itself. Tangent, rotate it 180 degrees, lands on top of itself. Cotangent, rotate 180 degrees, lands on top of itself. As a side note, in terms of going back to basic rotational stuff, in previous math classes, when you did rotations, usually you specify the direction. Well, what direction are you rotating in? For 180 degrees, you don't have to specify a direction. If you rotate 180 degrees clockwise versus 180 degrees counterclockwise, it takes you to the same place. For example, if we were to do 90, it doesn't apply here, but they do exist. A 90-degree rotation, you'd have to specify which way you're rotating, because a 90-degree rotation clockwise versus counterclockwise is going to give you a different result in the end. All right. Let's do just a couple quick numerical examples to illustrate that. So for the sine, we have the sine of negative u equal to negative sine of u. U could be a numerical value. It could be a single variable, or it could be an algebraic expression. This is valid for any of those options, assuming that what you're plugging in itself doesn't have any inherent issues with it. So what if we use pi over 2 as a numerical example to illustrate this? So if we use u is equal to pi over 2, that's the sine of negative pi over 2 equal to the negative sine of pi over 2. And we can use this graph to illustrate that they're both the same thing. So I'm going to do this one first. The sine of pi over 2 is 1. The negative sign makes it negative 1. The sine of negative pi over 2 is negative 1. So that's a numerical example to illustrate what we talked about graphically. Let's do one with the cosine. So the cosine of negative u is equal to the cosine of u. Oops, that's our property. Okay, for this example right here, let's try to get this to fit on the same screen here. Apologize, get this centered. Let's say use u as pi. So if we let u be pi, the cosine of negative pi is equal to the cosine of pi. So referring to the graph, when x is pi, cosine is negative 1. Cosine of negative pi, also negative 1. Now I picked easy to scale off these graphs with minimal computation. It's not always negative 1 equals negative 1. It just happened to be nice, clean, simple values that we could easily get from these graphs that didn't involve a lot of numerical computation. All right, I think that pretty much wraps it up for what we're covering today for this lesson.